this is almost over, and I'll just like relax.
It's that weird feeling of the finish line. You know it's there, and you know you probably get through it, and then it's like, yeah.
You're like, just like,
And this is the time when I pick up the pace,
right,
unfortunately.
simultaneously.
It's like, yeah, we have been doing warp, 5 or 6, for the earlier part of the semester. Now it's time to hit up to like warp 9.
Yeah.
Yeah, engineering, give me all the power you have. Divert all power to warp drive. Yeah. All right, well, 3 people it is, and I still have to get started. I cannot wait for the rest of the class. So this is what we are going to do today. We're going to talk about parameters. And as I said, all the topics now that I will be talking about all the way to the end, they all, quote unquote, stack up. Okay, and that's why it is super important to clear all the concepts at the end of a class. Um, and I'll give you guys some activities to do. Basically, understanding means you're making connections between the concepts. So, if the foundation concepts are well established, then you can also build additional concepts, on top of the foundational concepts. So, let's go ahead. So we're going to get into the parameters and local variables, but we'll focus on parameters today. And this is an older module that I wrote, some time ago, but it is still kind of important. Um, and I'm changing the format of how I wrote these modules. The old ones were written in LaTeX. The new ones were written in Markdown. You know, it's not like it should make a difference to you guys, but it's worth noting because you might see the styling may be different a little bit, but they're basically all the same. I need to clear my calendar because it's reminding me to be here. All right, cool. All right, so what we're going to do today is to look into parameters, and more specifically, we want to look into subroutines like this, okay? In other words, I'm just defining a C function that takes two parameters. X is one, y is the other one. They're both signed integers, and all it does is to return the difference between x and y. Okay, sounds pretty simple, right? Except we have not talked about how to do this in assembly language. So the question is, how do we pass parameters? I mean, passing parameters is a way for the caller to talk to the callee, right? So which document that we have already talked about so far do you think will at least describe a little bit of what to do about this? We got a caller, we got a callee, and this is something that requires both parties to have an understanding of each other. So which document do you think is going to be relevant for this discussion? I mean, obviously there's this module, but there's also a document that I talked about last week. And I said, well, this is something that we're not going to talk about yet. Okay, we'll just focus on the return address. That would be the caller callee agreement document. So that document also has been updated, just this morning a little bit to reflect, something that I thought, hey, if I make this improvement, I think the document would be easier to read. So let's go ahead and get to that document. So I kind of, made a new header of mutual agreement, so that this way we understand that this particular section, the entire section 1, is talking about things that both the caller and the callee have to agree to. And then I have 2 additional sections. One is callee only consideration. In other words, from the perspective of the function being called, what can it do, and as long as what restrictions are applicable. And then the third one is just basically a way to organize things. So we'll go back and focus on the mutual agreement first. And since we're talking about arguments, which is known as, okay, what is known as arguments from the caller's perspective are known as parameters from the function's perspective. Okay, so the names are slightly different. So from the caller side, if there are arguments, then arguments are pushed in reverse order. What that means is the last argument is pushed first. Okay? So the last argument is pushed first. So on the TTP architecture, arguments are pushed contiguously, which means there are no gap in between. The gaps are present when you're talking about the x86 architecture, because the x86 architecture is, even though it is theoretically byte addressable, which means I want to just get that byte. Okay, what is the address of that byte? However, when it comes to the actual organization of memory, you are retrieving at least 64 bits or 8 bytes at a time. And that is the reason why, it is not always a good idea to put things contiguously, because, then you might need two memory accesses to get to the same item. Okay? But in the TTP, it's not like that. It is byte addressable, and it only has a width of 8 bit, between the memory and the processor. All right, so if you push the last argument first, it also implies that the last argument has the highest address. Because when the stack is empty, the stack pointer is at the highest possible address. As we push, the first thing we do is to decrement the stack pointer. So that means as we add more items onto the stack pointer gets lower and lower, which also means, the first thing that you push on the stack is going to have a higher address than the last thing that you push on the stack. Does that all make sense? Because, this is actually going to connect. This is just connecting back to what we talked about last Wednesday. I know it has been 4 days, but that's what we talked about last Wednesday. Are we good so far with all of these concepts? Okay, very good. And that's it. Okay, this is the only addition to what we have talked about so far. Is the caller is responsible to push the arguments in reverse order, and then we push the return address. So you have to push every single argument in reverse order, and then we push the return address, and then we jump into the function that we're calling. So the tricky part is not so much on the caller side. The tricky part is on the callee side. So on the callee side, if there are arguments, so now we really need to get into this part. If there are arguments, the first argument starts at the address that is immediately after, in parentheses, higher than that of the return address. The last argument has the highest address, which we talked about already. And obviously, in this case, I was using the wrong term because they should be called parameters and not arguments. Are we still doing okay so far with this discussion of where the arguments go from the caller's perspective and from the callee's perspective as parameters, where they are situated on the stack? We good? All right. So now the question is, how do we get to those? Okay. So what we'll do is we are going to take a look at some sample programs as usual. And what we'll do is we're going to look at both actually, since I'm here already, might as well fix the note first, because on the callee side, all the terms of arguments should be parameters. So I'm just fixing all of these references to parameters, and I think that should be it. Okay. Save, and then render the HTML, and then upload it again. And now everything should be updated. So on the callee side, all the, no, it is not updated. Well, there are parameters. Oh, because these are singular, I only address the plural ones. Okay, so let's fix those two. I do apologize for doing this while I'm teaching, but if I don't do this, I'm gonna forget. So I'm gonna have to fix that and that. Okay. Okay, just double checking I got every single one in the callee. Okay, so one more time. There we go. And I think this time they should all be addressed. You can see how the argument was changed to a parameter, because I do want to make sure that I am using the correct term when I describe these items. All right, so we're back to the command line, because what I'm going to do now is to go to the temp folder. Actually, I need to get out of this, go to the temp folder, and what we'll do is we'll take a look at the C code and also take a look at the assembly code at the same time. So we'll just call this arg.c, arg.ttpsm, and it is in the wrong order. So let me flip it by using dash uppercase O, so they're side by side. There we go. All right. So on the C side, I'm going to have the account include stdint.h. So this way the program would actually compile if you want to compile that. Int8 underscore t simply means we have an 8-bit signed integer as a return type in this case, and we have subtract as a subroutine, and then each argument is also a signed 8-bit integer, okay, just like that. And the return statement is super easy. It's just x minus y. And then in main, we'll simply call subtract. Well, we can try out a few things. We can say 6 minus 14, and then return 0. All right, so this is the C code. Do we have any questions about the C code itself before we try to start to translate that into assembly code? C code is fine, okay? So we're going to transition to the assembly code. So in the assembly code, as usual, we start with a no op instruction, jmti to main, and then we leave a label for subtract. So this is the entry point of the subtract subroutine. This is the entry point of main. And when main is all done, we're going to get to a halt instruction because there's nothing else to do after main is all done. All right, so I just need to, I'm not seeing any reason why it's making that sound. All right, so the first thing we need to do in main, I forgot to do this a few times, is to initialize the stack pointer. So when I initialize the stack pointer to 0, it really means 256, except 256 is greater than 255, but because it wraps around, so when we decrement 1 from 0, we actually get back to 255. So this is the correct location to initialize the stack pointer with. All right, so from the C code, what we want to do is to call the subroutine with the 2 arguments. One is 14 and one is 6. So we have to first push the last argument, which is the 14, on the stack. On a x86 architecture, this is pretty much all you need to write if you want to push a constant value of 14. In TTP, it's a little bit more tedious because you have to manipulate the stack pointer directly. So you have to decrement D, reserve that space on the stack, LDIA with 14, so that because you cannot copy a constant to a location pointed to by a register, and that is a limitation by the architecture itself. So you have to put it into a register first, and then store register A to whatever register D is pointing to. So that is push 14, and then we're going to push the first argument, which is 6. Kind of the same deal, okay? Decrement D, LDIA with 6 this time, and then STDA. So now we have pushed both arguments. It is now time to push the return address. So this time I'm going to do something trickier than usual, but it's actually useful in the long run. So I'm going to do something like this, .5 plus stda, and that is pushing the return address. And then we can now jump to the subroutine, which is called subtract, like that. And when it comes back, we have to do 2 things. Because when it comes back, what is on the stack? If I ever get to this point here, just assuming this is actually pushing the return address, which is a big assumption, I will talk about that later. But assuming it does come back to this point, what is on the stack?
Is it 14 and 6?
Yep, they're still on the stack. Do we still need those two things on the stack now that the subroutine is all done?
No.
No, so we need to quote unquote deallocate those two items from the stack, which is not the same thing as a pop, because when you pop an item from the stack, it implies that you want to make use of the value that you just retrieved. In this case, I don't really care. Okay, these two things are just using stack space for no particular reason because the subroutine is all done. So it is the responsibility of the caller to deallocate the space used by arguments. And that can be done by using two increment instructions, like so. So now the caller part is all done. The callee part, on the other hand, is a little bit messier, okay? But we can always start with the actual return, okay? Because at the entry point of a subroutine or a function or a callee, we are guaranteed that the return address is pointed to by the stack pointer. That is always guaranteed. So that means, I can always start with something like this, LDBD, increment D, which is a pop. This is basically popping the return address into register B, and then the JMPB, so that we can continue execution in the caller. So this part is always relevant. It's always there. The question now is, okay, TAC, how do we get to those parameters? Remember, 14 and 6 from the perspective of the caller would correspond to X and Y as parameters from the perspective of the subroutine. So there are quite a few ways to do this because we know where they sit on the stack. If I were to draw a picture of what the stack would look like at this point, Y is going to be at the highest location that is relevant to this invocation of the subroutine. And right below Y is going to be X because Y was Y was pushed first, and then X was pushed, and then we have the return address that is also pushed, which means register D is pointing to the return address at this point, at the very entry point of the subroutine. So in order to get to X, okay, you might say, well, all we have to do is to increment D, then register D would be pointing to register X. That is correct, but it is also a very dangerous thing to do. Because do you still remember the discussion of the gremlins? Things that can modify everything on the stack that is below where the stack pointer points to. So the moment you increment the stack pointer, the one thing that it was pointing to is now susceptible to be modified by the gremlins, which are basically equivalent to interrupts in the actual world. Okay? So we don't want to do that. We don't want to change the stack pointer unless we're absolutely sure that whatever it's pointing to is no longer needed. Is that okay? So we don't want to use the stack pointer directly for any kind of calculation. So one thing we can do is to say CPR, pick one register, pick C, okay? So at this point, C and D are the same, which means if I want to document this, register C is now the address of the return address. Okay, it's just my way of documenting what is in register C at this point, because register D is still pointing at the return address. So when I make a copy of register D to register C now also has the address of the return address. Okay, well that sounds pretty good. So what I can now do is to say, now I can increment register C and not register D, because register C has no special meaning. Okay, according to the agreement between the caller and the callee, the subroutine being called can utilize register A, B, or C in any way it sees fit. So that means, hey, register C is just a register that we can use as a subroutine being called for whatever purpose I want to use it for. So in this case, I'm incrementing register C, and after the increment, register C is now the address of parameter X, which is relevant, related to what I want, but it is not what I want. Because I don't really want the address of X, according to the C code here, I want the value of X. So what instruction should I use to get the actual value of X, given that I have the address of X already in register C. I'll give you guys three choices: LDI, LD, or ST. LD is correct. Very good. Okay, so we use the LD instruction, and we stash it into one of the remaining two registers. In this case, I'll stash it into register A, and they go like, okay, so now A is the actual value of X because it is, oops, there you go, because it is the dereference of the address of X. So the asterisk and the ampersand, they kind of cancel out each other. So we actually get the value of X in register A at this point. Next, I'm going to increment C again, not D. So now C becomes the address of parameter Y, because parameter Y is 1 byte on top of parameter X. And I can do the same thing. This time I load it into register B instead. So now register B is the same as Y, because register C has the address of Y, and we are dereferencing it. Are we still doing okay so far? Do we have any questions up to this point? Do we have any questions about how the stack is structured? Do we have any questions about how the registers are being used? Do we have any questions about the instructions themselves, the mnemonic of the instructions? Okay, I'm gonna assume there are no questions. I don't see anyone, kind of turning the head or squinting like this. All right. Okay. So that means I have everything that I need because I have register A having the value of X, the parameter. I have register B being Y, the parameter. All I need to do is to subtract. And they're already in the right kind of registers because sub AB is going to subtract B, which is really parameter Y, from register A, which is parameter X, which is exactly what I want. I want X to be my middleware, I want Y to be my subtrahend, and this setup gets the whole job done. And since register A is also supposed to be the register that I should use in order to return a scalar value, everything is in the right place now. So it's time to return, and I already got the return instructions, the LDBD, increment D, and JMPB. That's the return. Those three instructions are responsible for actually returning to the caller. So I think I'm done. Do we have any questions before I test run the program? No questions? All right. So let's go ahead and test run this program. And the way we're going to do that is to utilize River Spider, because it's just super handy to have. I'm hoping that demonstrating how handy that thing is will convince some of you to spend maybe 15 minutes, half an hour or so to set it up on your own computer or set it on a thumb drive so you can actually use it when you are in the lab. Because once we have everything set up, it's just one command to submit the file, which in this case I think is called arg. Okay, did I forget the name? What was the name that I used? It was arg, but where is it? Oh, I forgot to save it, that's why. Now it has it. ARG, there we go. All right, so let's see if I made some silly mistakes, like syntax errors and using the wrong labels and whatnot. So everything is good, running the simulator, everything is all done. All right, so we got a few mystery items to check out this time. So let's go ahead and check out those mystery items. And I actually do not have the assembler opened. Okay, so this is all done without actually having the assembler in the browser, and yet it can get everything done. So we'll go to my drive. Okay. and go to the class, and you go to shared. So if you want to open it on your side, it should be there already as well. So we go to processor, and then we go to the assembler, and then we go to the, well, we want to double check everything first. So we want to check the source tab and make sure that's the program that we have written. That's all good. And the mystery item in this case is, what is this doing? Well, I talked about the postfix notation already. In other words, we always specify what we are trying to do with before we specify how we want to do it. Okay? So in this case, the dot, whatever is representing a number. 5 is representing another number. And the plus is simply saying, okay, we got two numbers, I can add now. So the question is, what is the dot representing? The dot is representing the address of the instruction where the dot is. Okay, let me say that one more time. The dot is representing the address of the instruction where the dot is. So on this line, on line 29, the dot is basically the address of the LDI instruction. Is that okay? So there's a way to refer to the address of the instruction where the dot notation is. So why am I adding 5 to it? Okay, that's the next question. So that's because LDI itself takes up 2 bytes. So dot plus 0, dot plus 1 would be on line 29. Dot plus 2 is line 30. Dot plus 3, dot plus 4 would be line 31 because JMPI also takes up 2 bytes. So dot plus 5 is going to be on line 32. I do apologize. Nope. Okay. Let me see. Did I turn off? Nope. Do not disturb actually did not turn on automatically. Now it's on. All right. So are we good so far? So byte 0, byte 1, byte 2, byte 3, byte 4. This is byte 5. Is that okay? So dot 5 plus is basically saying, what is the address 5 bytes away from the instruction of the line where the dot is referring to? That's all it says. Is that okay? So why do you think I would prefer to use this approach rather than the approach of using a label? Remember, last week we have been using the labels, return point 1, return point 2, and so on. So what is the problem of the label approach? What if I point to the wrong label? What if I refer to the wrong label? The wrong label being a label that is also defined, but it's not the right one that I should be referring to. The assembler says, okay, syntactically, it's not a problem. It is not undefined, but the behavior of the program is going to be wrong because it's going to end up at the wrong place when a subroutine returns.
So it would be harder to find a bug that way?
It would be kind of hard to find, unless you know this is the kind of mistake that you tend to make, that makes it easier. But it will be harder to find, yes, okay? But this way it's a little bit easier because, as long as you keep these instructions kind of the same way every single time you call a subroutine, I mean, they're pretty, these 4 instructions are reliable when they're together like that. Is that okay? All right, so now that we know the program looks right, let's go to the Assemble tab just to make sure that line 29 get assembled in the correct way. So we go to the Assemble tab, we scroll down to the LDI instruction, which is line 29. The location itself is 17 in hexadecimal, and 17 plus 5 is 1C, I believe, which is over here, and that is the correct place to return to. And you can also see how 1C is also the second byte of the LDI instruction, because that is the constant that we are going to load into register A before we push it on the stack. Is that okay? All right. So the next question is, did the program work? I mean, how do we know whether the program worked or not? I think this is new to this class. I actually enhanced the tracer, so it also includes column F, which is the line number, and also column G, which is quoting the actual source code of that line. I think that makes it much easier for you guys to kind of follow and kind of understand what is going on. So on line 1, we have the no op instruction. On line 2, we have the JMPI to main. And then on line 19, which is the line after the main label, we have the initialization of the register D, which ends up with register D getting a value of 0. And then the next instruction is immediately decrementing D because we want to push, and that term register D to FF. And then we have an LDIA with 14 because we want to push 14 on the stack. And this is why register A get a value of 0E in hexadecimal because E is 14 in hexadecimal. And then we store whatever register A has to the location that register D is pointing to. Register D has a value of FF, and this is why location FF in RAM is now changed or overwritten with 0E as a value. This is my second argument. And then we do the same thing with the first argument. We end up with 06 being stored to location FE. And then we push the return address, which we just verified is at location 1C. So 1C is now also pushed onto the stack. At this point, 3 locations on the stack are being used. The top one is the 14, the second to the top one is the 6, and then the third to the top is going to be the return address. And this is where we perform the unconditional branch to subtract, which is the entry point of the subroutine or function. And then the first thing we do in the function is to copy register D to register C, which ends up with register C having FD as its content, because register D has the value of FD already. So now register C is having the same thing. And then we increment, which turns register C to FE. But FE, at location FE, that's where we find the 6. Okay? So one indirect access using the LD instruction, we end up getting the value of 6 at location FE into register A. We increment C again, and now it is FF, and we know what is in FF. FF has the 14. So when we do the LDBC, it uses B as a pointer to point to the location FF, and it retrieves the content at location FF, which is our F0E, and it put it into register B. And then, now that we have register A having X, which is 6, register B having 14, and that is Y, we can now perform the subtraction. The subtraction result is F8, which is -8. This is the signed representation of -8. How do I know that? How? Yes?
Because the sign bit is 1.
Mm-hmm. So we know it's negative.
And it begins with F, so in hexadecimal that's 15?
F is the last one. So in base 16, the last
16.
digit is 15.
Oh, it's 15.
So F is 15.
So F is 15.
Which is
8,
1.
So it's 8 minus 15?
Not quite. Not quite. So let me see if I can get my text editor. Yep, there we go. I'll copy my text editor here, get a new document. All right, so F8 in hexadecimal is 11111000 in binary. So there are 2 ways to look at this. The first way is simply to look at all the ones and figure out what we're going to do with all the ones. So one way to look at this is we have no 1, no 2, no 4. We have 18, we have 116, we have 132, we have 164, and we have a subtraction of 128. because the 128 is corresponding to this bit over here. So this is the only difference between the interpretation of an unsigned value versus a signed value. With an unsigned value, everything is added, including the power of 2 represented by the most significant bit.
Right.
But in a signed interpretation, the bit corresponding to the most significant bit, that is subtracted. So if you do the actual math here, it is going to be -8.
Right.
The other way to look at this is -1 is all ones, right? So you just kind of step backward, and it will take eight times to get to F8. So we know it's -8. So there are two ways to look at that. But 6 minus 14 is indeed -8. So we got the right result, right? And let's see if the sign flag is set, okay? Because in the subtraction, it should also set the sign flag. So
I think it's in column E. Yeah.
Yep, so you can see the sign flag is a 1, the carry flag is also a 1, that is correct, and then the L flag is also a 1. But we are not done yet, okay? We have just finished the computation. It is in register A, which is all good. And then we get to line 14, which is retrieving the return address. So we get the 1C into register B. We increment D because we're supposed to pop the return address, and that's why we have to increment the stack pointer. So the stack pointer now becomes FE. And then the JMPB instruction will take whatever register B has, and we will continue execution at that location. So that's why it continues execution at location 1C, where we find an increment D instruction, because at this point, the two arguments are still sitting on the stack, and they really have no particular value being on the stack. So we increment D twice to get rid of the two arguments. And by the time we get to the halt instruction, register D is back to 0, 0, which means the stack is indeed balanced. And that concludes the execution. Do we have any questions about this entire thing? Or any questions about, but how am I supposed to study this? So I think I did this with the Thursday class, but not this class. So I will do the same thing in this class. Is how do we look at all of this stuff here and quote unquote study for this class? There's nothing to memorize. Okay, the final exam is open book, open notes, just like the first two exams. So that means if there's anything you think you might forget and it is actually useful, such as the opcode table, the processor architecture, and all the sample programs that have ever worked on, if you keep track of all the spreadsheets, you can print them out. You can bring all of those with you. But it's not going to be as helpful unless you understand the concept already. So the question is, what does it mean when I understand something? It doesn't mean that, when you listen to my lecture, this lecture again, that you seem to get everything, because that is the operative word here is seem, okay? So what you need to do is to make connections. So that means what you need to do is to go to the source tab here and explain to yourself what each line is doing. What is the purpose of each line? Now, when I say that, I do not mean that you go to the subtract subroutine here and just say, I'm copying the value of register D to register C. That's exactly what it's doing. But what is the context? What is the purpose? Why are we doing this? Okay? So it's not just a question of what the instruction is, it is also asking in the broader context of why we are doing it. Well, the reason why we're doing it is because we want to use register C to retrieve the arguments. So that sentence is connecting the instruction to the concepts. What concepts are we talking about? There are at least two concepts that are involved here. One is relating to the concept of parameters in C and C++. The second one is both of those things, both of the arguments are on the stack, and that's why we have to make a copy of the stack pointer. Is that okay? All right? And unless I make a mistake, I'm still recording now. So, so everything is still being recorded. The time is 11:10 at this point. So what about the next line? Well, the next line is increment C. Why do we want to increment C? To explain what is increment C is easy. You go to the opcode table, it says, oh, we are just adding one to a register without affecting the flag's register. Fine. But why are we doing it? Okay, it is the why that is important. The why is also what is connecting between all the concepts. We are adding one to register C because we want to get to the address of parameter X. But why increment C? Because it has to do with how the caller is putting the arguments on the stack relative to the return address. That is why.
So the what and the why.
The what and the why, and then the why eventually has to connect to the C concept, okay, of arguments. But everything relates to the stack. In other words, how are things organized on the stack? We know the arguments are on the stack, but how are they organized? If I have two arguments, which one has the higher address? Which one has the lower address? And why is it the case? Okay, so all of those are the questions that you need to ask. And if you can answer all of those questions kind of without thinking much about it, then I would say you have probably a good understanding of the material. Are we doing okay so far? So it is tedious because you have to do it with every single instruction, at least for the first few programs. You're going to have to do it to every single line of code. So that way you start to build up your own association in your mind. Because once you understand it, you probably really don't need the sheets of paper to bring to the final exam. You probably want to do that just to make sure that if I ever need it, it's there. But once you understand the concept, you probably won't need to look it up too often. So that's the first part, okay, is to look at the source code and document the source code itself and explain what each line is doing and why we are doing it. How does it connect to the C++ or the C program itself? Then the second thing you do is to relate the source code to the analysis tab. Now that the analysis tab actually quotes which line we're on, including all the comments, that should really help, okay? But when you're in the analysis tab, there's one thing you can also do, is you can, at any time, you can now track what the stack looks like. Is the stack empty? Or if the stack is not empty, what is on the stack? So I will give you an idea, okay? I'm going to give you an idea whether you guys want to do it or not. It's up to you. So I'm just going to use square bracket like this to indicate the stack is empty at this point. And at this point, when I overwrite this location with E, then I need to line up everything. So now the stack has one item, which is FE on the stack. And over here, we have two items on the stack. So we have FE at the top of the stack, at the bottom of the stack, because it's actually the other way around. And then oh, nope, I take it back, sorry. This is actually FE, not 0E, not FE, because I want to look at the content on the stack. So the content is 0E, not FE. And then over here, we have 6. So now we have two items on the stack. And then at the next point, we will have 3 items on the stack. So we have FE, 0E, sorry, I keep saying FE, but it's 0E, 06, and now 1C also on the stack. Okay, so the top of the stack is always on the right-hand side or the right side. That's up to you, okay? Whatever standard you want to use is up to you. Just use a consistent way of documenting what is on the stack. So now, in this case, you have to kind of document, what register C is pointing to. So, I know it's not easy because you're trying to keep track of something that is dynamically changing as you execute the program. But what you need to do is to visualize the stack as the instructions go. You can draw pictures, okay? Your pictures would be pretty easy to do. The only tricky part of a picture is you have to draw multiple pictures. Think of the pictures as frames of an anime, okay? Because we are changing the stack content dynamically. We're changing the stack pointer also dynamically. So you kind of need to visualize that it is something that's changing all the time. And at one particular moment of time, what does it look like at that moment of time? Is that okay? So how you want to look at this or how you want to represent it is up to you, because some people, like myself, prefer to kind of conceptually understand the whole thing, so I can actually see, I can see in my mind's eye, where things are. But if you're more graphical, you can draw a picture. So that's kind of what I would do, is to track the content on the stack as the program executes. So I would heavily utilize what is column C and also what is in column D, because column C reflects all the actual update of locations in RAM, and then column D reflects all the updates of the registers. So you can actually see when a particular instruction executes, this is what happens at runtime. Is that okay? So that's another piece of quote unquote understanding, is to connect what you see in the trace with the instructions, and also in return, connect all of those operations to the stack concept as well as to the C++ concept. Are we doing okay so far with this discussion? Maybe. Hopefully. All right. Well, I think we got enough to implement string length now. And then you guys will say, but Tag, you haven't even talked about local variables. How can you do string length without any local variables? The answer is, I can do it by recursion. How about power of 2? Would that be easier? Let's do that. Let's do that. I'm just excited about doing this. String length I've done many times here, so we'll do something I haven't done before. So we'll look at power of 2. I'll just call it p2.c and then p2.ttp-asm, and we'll put both of those in the temp folder, because I don't want to clutter my other folders. Okay, so we'll go ahead and pound include stdint.h. So we'll have uint 8 underscore t, p2 uint 8 underscore t. This is n. So p2, okay, let me comment here. P2 returns 2 to the power of n. That's what it's supposed to do. And the way to do that is to use recursion, because if I were to do this with a loop, I probably need to use local variables to keep track of which iteration we're in and so on and so forth. But if I do it with recursion, I don't need to do that, because n is its own counter, and I don't need a temporary variable to store the result, because I can specify the return value right away. All right, so the special case here is when n equals to 0. If n equals to 0, 2 to the power of 0 is just 1. This is where we can stop the recursion. Otherwise, we are going to say 2 times p2 of n minus 1. Okay? And I know somebody's going to complain and go like, Tag, but we haven't really talked about multiplication, because there's no such thing as multiplication in the processor. That is true. But to multiply something by 2 is just adding it to itself. Okay? We can do that. That's pretty easy to do. So that's the trick I'm going to use here. Okay, so in main, I'm just going to call p2 with, well, let's say 5. Okay, 2 to the power of 5 is 32. So we're expecting register A to end up with 32 when this is all done. And then we turn 0 over here. So that's the C code. Now we look at the assembly code. Okay, start with the no op, jmpi to main, all the usual stuff. P2 is the entry point of the subroutine. And I personally prefer to always have a little map here to look at what is on the stack at this point. And then we can also just kind of by default include the return instructions so that we can have the code to return to the caller. So LDBD increment D, and then JMPB, like that. And then in main, we have a halt at the end, and then we do a LDID with 0 to initialize the stack pointer. And now we have to push 5 on the stack. I think at this point, we kind of know the drill already. Decrement D, LDIA with whatever we are trying to push, ST, which is store, to whatever D is pointing to, whatever is in A. And now we have to specify the return address. So decrement D, LDI, A.5 plus, STDA, and then we can JMPI to the subroutine, which is P2. When it comes back, we have to remember to deallocate the one argument that is still sitting on the stack. So that's an increment D. All right, so I got the framework already set up now. The question is, so how are we going to deal with that return statement in P2? Because that is the essence of this entire program, is the only one statement inside the subroutine P2. Yep.
This is LDI A dot 5 plus.
Okay, so we explained that earlier in today's lecture. You might have missed that part. The dot is the address of the instruction where the dot is on. Okay. So it is computing the address that is 5 bytes away from the LDI instruction itself, okay, which is where it needs to come back to. So it's a much more concise way to, instead of using a label, it's just a much more concise way to compute the return address. All right. So if you have time, if you go back to the beginning of the lecture, you will see that whole discussion. Okay. All right. So now we get back to P2, and then we go like, what are we going to do here? It would appear that we need to get to N. So we can do the same trick, which is CPR CD. So now you'll see this is what I would do, is to relate what is in a register being changed by a certain instruction to the C concept. So this is going to be the address of the return address. Increment C, C. C is now the address of the only parameter in this case, which is N. But I don't need N, I don't need the address of N, I need the value of N. And looking at this, I don't think I need to access the address of N from this point on. So I can just do a LDCC. So now C is actually the value of parameter N. And now I can compare that to 0. But to compare, to use CMP, we need to set up another register because the only thing, it can only compare two registers. You cannot compare a register to a constant, which is kind of a bother, okay, because now we need to set up another register. But if you remember from an earlier lab activity, if you just want to check whether it's 0 or not, that's a shortcut way to do it, which is using the AND instruction so that we can say AND CC, because this basically just pushes the value of C through the ALU, and because it's not increment or decrement, it does affect the flags, okay, particularly the sign and also the Z flag. So the Z flag will reflect whether register C is 0 or not, which is all I need. So I don't need to set up the full thing for compare instruction. I can just use AND CC to do the same thing. So JCI, which is the only conditional branch that I can use that relates to the Z flag. So if it is a 0, I have to go somewhere, and that somewhere is going to say return a 1. I'm just going to go ahead and say return a 1. Otherwise, we're doing the recursive call. So this is where we do the recursive call, and ret1 is over here, which means we just have to return a 1. Returning a 1 is easy. LDI A with 1, that's how we return 1, because register A is what we use to return a scalar return value. And I also need to merge the two branches. So this is basically return to caller, because this one here needs to skip over returning a constant of 1 to return to caller. In other words, this is an if-then-else construct. It's just that in C, it is expressed as one single expression, but in assembly language, it has exactly the same construct as an if-then-else statement. Are we still doing okay so far? Yes? Okay, all right. So in the recursive call, what are we going to do? Well, I'm going to call P2 again, but this time I use n minus 1 as my argument. Fortunately, C, register C, still has the value of parameter n, so I'm just emphasizing it here. Register C still has n in it, okay? So that means if I just do a decrement C, then C is now n minus 1, and we just have to decrement D, ST, D, C. This is pushing n minus 1 on the stack, and then we have to call the subroutine again. Oh, no. Okay, let me just stop here and be a little bit dramatic. Oh, no, we are in the subroutine that we're supposed to call. What are we going to do? And to quote the brain in Pinky and the Brain, the same thing that we always do. Push the return address and then JMPI to the subroutine. But Pinky is going to say, but Brain, it's the same subroutine that we're in right now. Brain's going to say, it doesn't make any difference. We do the same thing every time we call a subroutine. All right? Now, this is important, okay? This is really important because this is why some people do not understand recursion. It's not because they're not smart or they're not intelligent or they're not hardworking. It's because they overthink. Okay? Overthinking is the first and most important obstacle of understanding recursion. Okay? If you're doing a recursive call, it's just the same as calling any subroutine. Okay? So it's going to be the same thing. Push the argument, and then what do we do? Push the return address. So I can still use register A at this point. Register A has no particular special meaning. STDA. And then we branch to the subroutine that we're calling, which just so happens to be P2, okay? And then increment D to get rid of the argument after it returns. But at this point, register A is going to have the value of P2 of n minus 1 already. That's close to what I want, because remember, what we need to return is not P2 of n minus 1, but twice that, right? What do I need to do at this point? I already got P2 of n minus 1 in register A. Yep.
You can add A to A.
Add A to A, exactly. That's all we need to do. Add AA, okay? Just to comment, A is now 2 times P2 of n minus 1. And I just do an unconditional branch. Otherwise, I'll be overwriting that thing that we just computed, with a 1. I don't want to do that. I'm just going to jump around the code to return a constant of 1. And now we get to the actual code to return to the caller. I think it's going to work. All right. Do we have any questions? No questions? Okay. So how much stack space do you think this program is going to use? Yes, there was a question like that in one of the labs last week, but this time I want you to figure it out. We are starting with n being 5. The stack was empty when we got to main. So the question is, how many bytes on the stack are we going to consume at the maximum? In other words, how many locations are absolutely needed in order for this program to work on the stack? So how would you approach this problem? Well, I would approach this problem, probably with a picture of some kind, okay? It doesn't have to be a picture, but it does have to be somewhat pictorial. So every time we call P2, okay, we need 2 bytes, okay? 1 byte is stored to store the argument or the parameter of n, 1 byte to store the return address, okay? This is called a frame, a call frame, okay? That's one word to refer to it. Everything that a specific invocation of a subroutine needs on the stack is called a call frame. In this case, we have a pretty simple subroutine. It's one single parameter, 1 byte for the return address, and that's it. So now the question is, how many levels of P2 do I have when it's at the deepest part of the recursion? So now you have to say, all right, so let's check that out. We start with n equals to 5, right? Okay, that's the call from main. And then it gets down to 4. And I'll just do the lazy thing of getting the exponential growth that I need. We got the 3, we got the 2, and then we got the 1 and the 0. And this is when we stop. So that means it uses up 12 bytes on the stack. Because we have 6 invocations, and the 6 invocations are on top of each other. Each invocation takes 2 bytes. 6 times 2 is 12. Is that okay? All right. So now we're gonna test run this program. Okay. Let's see if I make some stupid mistakes or not. All right. So we're gonna get back to. Nope, not this one. Huh. Okay. Well, I suppose we can use this one. All right, so we submit, this is p2.ttpasm, and once again, I forgot to save it first. Let's go ahead and save it. Nope. There we go. And you can actually see the assembler doing its computation thing in the background, because every time it gets updated, there's a little progress bar over there. All right, so let's switch back to the assembler and go to the analysis tab. If you're impatient like myself, you can always skip to the end of the entire trace just to look at register A, C, and see whether it is 32 or not. Okay, quick question. What is the hexadecimal representation of 32? This one is super easy. 20, very good, because the 2 is representing the number of 16s, and 32 turns out to be 2 16s. So that's a pretty easy one to convert. All right, so the summary tab will give you the length of the trace. So it has a length of 196 lines. So now we just have to go to 196, right? So you can actually enter the 196. And now we got to the end, and register A, the last time we modify register A, we put 20 in hexadecimal into it, so we got the right answer. Second question, did we kind of balance the stack okay? Yep, we did, because register D went back to 0, 0. Third question, how do we know that we used up 12 bytes on the stack? How do we know that? Well, there are a few ways to do this. You can always just do the manual counting thing and just look at column C and then just look at the lowest address that is written to and then subtract that much from 0, 0, and the difference would be the number of bytes being used. So you can do it that way. It's just really kind of tedious because you have to kind of scan through this whole thing and then find out, how we, overwrote, content on the stack. So as it turns out, the last location that we overwrite in memory is F4. So if you subtract F4 from 1, 0, 0, it is indeed C, which is 12. So we got confirmation of everything. Are we doing okay so far with this program? This might be the first time you actually see recursion in assembly language. And over time, I'm not saying it's going to happen today, but over time, you would find that when you look at the execution of a recursive function in assembly language, it actually helps to understand how recursion works in general. Because you can now see every call, every invocation has its own little structure called a call frame that is independent from all of the other invocations. So that means each invocation has its own arguments, has its own local variables, and also has its own return address. All right. Any questions about this particular program? Okay. Well, we still got about 10, 15 minutes left. I'm going to go back to the first program and address one particular issue with that program. This subtract is ugly, okay? I call this ugly because the way I compute the address of x and y is really, quote unquote, organic, okay? I'm just using a register C and moving around to get to the right place and then dereference when it's at the right place. So that means, in your mind, when you're writing this code, you really have to track where register C is, okay? Okay, it's over here, but I need the byte on top of that. I need to increment, or I need the other byte back. You have to decrement, and so on. So that's a lot of trouble. So what I'm going to do is to look at this and go like, that doesn't look good. And I'm going to re-implement subtract. So I'm going to re-implement subtract. But this time, I'm going to use symbolic names to refer to all the different things on the stack as offset from the beginning, as offsets from the stack pointer itself. Okay, so there are a few things, and I'm going to prefix everything with subtract because you can only have, okay, TTP-ASM can only handle one source file, which means all the labels are within the same namespace. And as a result, if you don't prefix names with the function itself, it's very easy for you to run into a problem of, you're using the same label when you're not supposed to. So I'm just going to prefix the label with the name of the function. So we're going to start with the return address. In this case, it is defined to be 0 because that's where the stack pointer points to, okay? Because the register D is pointing to the return address. The next thing on the stack is going to be parameter x. So that's going to be subtract x, and that's going to be, and some of you may say, oh, okay, it should be 1 because it's 1 byte away from where the stack pointer is pointing to. That would have been correct, but it's not the best way to do it. I'm going to do it the long way, which is subtract return address 1 plus. So now everything is relative, okay? I can change the definition of subtract underscore return address, and then x is going to float with it. It will change accordingly. And I have another parameter, which is y, which is 1 byte after x, and that's how I would represent it. So these labels, subtract underscore return address, subtract underscore x, and also subtract underscore y, they are not your variables, okay? They are merely offsets or displacements from where on the stack can I expect to find these items. This is representing the number of bytes away from where the stack pointer points to. Is that okay? Okay? All right, if that is the case, what are we going to do in the subroutine? Well, we need to access x, we need to access y. So the typical way that I would do this is to do a CPR CD. So I'm still copying register D to register C. Actually, I take it back. Forget that. I take it back. So the way I typically do it is to load the label into one of the registers. So in this case, I would load the first one into register A, subtract underscore x. So at this point, register A is offset to access register x, not register, but parameter x. And then I'm going to add AD. So now register A becomes the address of parameter D. Okay, I'm just going to pause here and see if that makes sense to you. The label subtract underscore x is representing the number of bytes as an offset from where the stack pointer points to until I can find x. So it's an offset. By itself, it is not an address. It is simply an offset. So the reference point is always where the stack pointer is pointing to. So that's why I have to add the offset to the stack pointer itself. Then it becomes the address. It becomes an actual address. Is that okay? I can give you one analogy. I can say, so I can now say, Rayshawn, lives 5 houses down from my house. Okay. So if you only know that information, can you find Rayshawn?
No.
What if you also know my address, where my house is? Then you can say, oh, okay, I can find Tax's house, and since Rayshawn's house is 5 houses down from his house, I can now just go like count 1, 2, 3, 4, 5. That's where Rayshawn lives. Is that okay? So the label is only storing that 5, okay? It's 5 houses down from where Tax lives. Tax, on the other hand, is where the stack pointer is pointing to. My house is pointed to by the stack pointer. So that's why you always have to add the stack pointer to the offset in order to get to the address. All right? Moving on. So that's just the address, which is not really what I want because I want the value. So LDAA will do the trick. So A is now the actual value of X. So how should I access Y as a parameter? The same thing, okay? The fact that, I'm just going to use the same thing. I know it looks really redundant, but this is a way where it is a reliable way to find and access items on the stack. So I'm just going to claim that at this point, register B has the value of parameter Y. So now I have all of these items. I can now just do a subtract AB because I'm supposed to compute X minus Y and use that as a return value. And then we can just go ahead and do the usual return stuff, which is LDBD, increment D, and then JMPB, like so. So I'm claiming this new subtract would also get the same thing done. So what I can do now is I can rename the other one as underscore underscore subtract. So it's no longer being referenced by main. Instead, main is going to reference the second definition of subtract. But before I run the program, I want to see if there are any questions about this approach. So which approach do you like better? The first one, where things are kind of more organic, you kind of have to keep track of where register C is pointing to, and also kind of where things are. And then you have to remember, Y is one byte on top of X, and then or X is 1 byte below Y. Whereas the second approach says, we'll just use symbolic names to remember the offset of these various items relative to where the stack pointer points to. So which one do you think is easier to read?
It's like pick your poison.
Except one is not. One is just kind of bitter. The second approach is what I would choose because it is using symbolic names. It's easier to look at the assembly code and be able to associate the assembly code back to the C code. Okay, the first one, if you just look at the assembly code, it doesn't really tell you without a comment, without these 3 lines. Okay, well, we can try that, right? All right. No comments. I think right now you still kind of retain what we talked about earlier, and you can still kind of understand that code. Try this again tomorrow, or just 6 hours from now. It's hard to keep track of things, right? Whereas with the second one, even if I take out all the comments, just by using the name of subtract underscore x and the name of subtract underscore y, at least I know, oh, we are trying to get to x, oh, we are trying to get to y, and so on. And we don't have to kind of remember how they are ordered on the stack because that's all taken care of when we defined the labels. So the second approach is what I would choose to use. The first one is great for explaining how things are organized on the stack. So between these two versions of subtract, which one is part of the um, caller-callee agreement? The answer is a trick question because none is. The caller-callee agreement doesn't care or specify how the callee is supposed to access items on the stack. The callee can choose whatever obscure way that it wants to access items on the stack. As long as it can still get to those locations and get the job done, the caller doesn't care. It's like, all right, this is a book. You want to read it backward or forward, or start in the middle, it doesn't matter. Okay, because it's from the caller's perspective, that's all up to the callee to decide. All right, so let's go ahead and run the second version of the subtract um, program, and just to see whether it still gets the job done or not. So it's going to be arg.ttp-asm. All right, so we switch back, and we want to find out how long the trace is. 47 lines, so we just go ahead and go to row 47. All right. And we just have to look up what A got as the last update. Well, it's still F8, so it still got the job done. So I would also extend what I suggested you guys to do to also to cover this program. So there are 3 sample programs that I wrote today, and I think it would be probably useful to do the same thing, which is commenting the program, the source code, as well as the analysis tab, and connect what you see in the assembler to the concepts. Okay, so the concepts that we are talking about here is first how the stack is utilized, and then second is how that relate eventually to C++ concepts. Call versus return, where's the return address? How do we push the arguments? How do we access the parameters from the perspective of the callee? All of those are concepts that we talked about today. The program is here to illustrate exactly what instructions we use, but you have to make that connection between the instructions and also the concept that was being discussed here. Are there any questions before I kind of stop the lecture? Because I think this is one of those days where I can actually end the lecture on time. We all good here? I would suggest you guys to draw pictures, okay? Because drawing a picture of what is on the stack and which line is responsible to put what item on the stack or how to change the stack pointer, that is really important. All right? So I'm going to give you the lab for today. So the lab of today is params and return value. This is the lab. I set up everything already, so all I have to do is to unhide it. The access code is frame, F-R-A-M-E, all lowercase, F-R-A-M-E. So frame is the access code. The lab is now released. So once you refresh your browser, you should be able to get to the lab for today. Any other questions before I stop the recorder? It's still going right now. No questions? All right.